All right, now that we've discussed integration by parts, let's go ahead and look at a particular problem that might present some unique issues. So let's let's try to look at this problem here, and we see that right away it doesn't look like any previous method for integrating would apply here. It doesn't appear that we can use U substitution, or nor does it look like it's going to result in an inverse trig function or so on. So integration by parts seems to be the way to go. So the next part then is to think about, okay, which factor of our integrand would make the most sense to be our u, and which would we want to have be our dv? And looking at this carefully, it would probably make the most sense to have this be our u here, and sine of 2x dx would make the most sense to be our dv. So I'll write u is equal to x squared. That means du is equal to 2x dx. And that means dv, if that's equal to sine of 2x dx, then v, the integral of sine 2x dx, would just simply be negative 1/2 cosine of 2x. So using the formula ultraviolet integral of v du, we would say u times v, so x squared times negative 1/2 cosine of 2x minus the integral of v times du. So that would be 2x dx. Okay, and I could actually put the parentheses maybe around the 2x just to make this a little less confusing. All right, so we have that here. And then now we see this integral, and we have to look at this and try to integrate that. But if you're looking at that carefully, and even if we clean this up a little bit and said, let's say this was negative x squared over 2 cosine of 2x, and we can move that negative 1/2 to the outside, so that's plus 1/2 cosine of 2x times 2x dx. If we're looking at that, this also appears to be an integral where u substitution also wouldn't work. And in other words, we would have to use integration by parts again. So this is a repeated integration by parts problem. So you could sit here and we could try to redefine these values. We could say, all right, well, it would probably make sense then that this here would be our u, and this here would be our dv. But if you're looking at that, the one thing that we have to be a little careful about is that we already defined u as being equal to x squared. So we'd have to redefine this as u sub 2, call this some other variable. And in the same way, also make this dv sub 2. And that can get a little unwieldy and a little bit trickier to keep track of. On top of that, we may then again get another integral where we have to do integration by parts again, because we know that the integral of cosine is going to result in sine, the negative sign. So there's a very good chance we may have to do integration by parts again. And so there's a chance that we may have to continue to use integration by parts as a technique. Fortunately for us, there is a method called the tabular method that helps really organize this process. So the tabular method starts by us setting up a table, hence the name, the tabular method. So let me go through how the tabular method works. So we would go ahead and in the first column, we are going to write alternating signs. And I'll talk a little bit about why these are alternating in just a bit. In the second column, we start with whatever our u was. So our u was equal to x squared. And then our du, or u prime, is equal to 2x. Then we're going to continue to differentiate down this column. And so u double prime, or the second derivative, is 2. And u triple prime, or the third derivative, is going to be equal to 0. So the second column is reserved for u and all of its higher order derivatives. The third column then has us writing dv. So we said dv was sine of 2x dx. And we're going to integrate this as we go along. So the integral of sine of 2x is negative 1/2 cosine of 2x. This is negative 1/4 sine of 2x. And the integral of that is 1/8 cosine of 2x. Okay, so we've just set up the tabular method. So how does this work? Well, what we're going to do is we are going to multiply u by what is v. Remember, this is actually our v here. So we're going to do u times v. Remember, that's the beginning part of our integration by parts, uv. So we're actually going to multiply these two values. So again, that would give us x squared times negative 1/2 cosine of 2x. And we've already done this, but I just want to show you how we would get the same integral from doing the tabular method. All right, next. we're then going to multiply du, or 2x, by the integral of our v. And we're also going to take into account that this is subtracting, or we're going to play a negative here. So that, in other words, we're going to write this as minus 2x times negative 1/4 sine of 2x. Well, why are we applying a negative sign here? And it goes back to us remembering that we are subtracting this. Okay, we're subtracting the result of integrating v times du. So this is our new v, if you will, by du. Okay, so we're subtracting that there. And then we're going to continue to go along in this process. We're then going to go to positive 2 times 1/8 cosine 2x. So plus 2 times 1/8 cosine of 2x. And notice here that now in our next row, we get 0. And so really, it doesn't matter. We don't have to integrate anymore. We can stop integrating because we can no longer differentiate anymore. Or another way of saying this is that since our derivative here is 0, it doesn't matter what we multiply by. So we know that we're done. So we're just going to go ahead and stop there. Okay. And something that I really want to highlight, just quite literally, is understanding that the product of any row, or integrating the product of any row, is going to be the sum of all of these diagonal products that we get. The product of this row is x squared times sine of 2x dx. The integral of the product of this row here that I've highlighted in yellow is going to be the result of multiplying x squared by negative 1/2 cosine 2x and adding up all of these diagonal products. Okay, so if we kind of compare and color coordinate what we have with every single step of the way, the integral, we see that x squared times negative 1/2 cosine 2x was our u, and we're continuing on with the tabular method. Okay, so when does the tabular method work? When is it a good idea to actually do the tabular method? It's a great idea whenever one factor of our integrand is a polynomial. It's a polynomial function with some higher order derivative ultimately resulting in 0, because we end up with 0 here. But when we have a situation where both factors of our integrand are transcendental and neither are polynomial functions, then in those cases, while the tabular method could certainly work, it may not be the most obvious method of how to actually go about doing those problems. So an example of this might be something later on in the lesson, something like e to the x times sine x. Integrating that, we could use the tabular method, but not quite sure it's really the best or cleanest option there. But I will talk about that in the next video. So just to make sure that we're comfortable with the tabular method, let's try another problem. Let's go ahead and use the tabular method to integrate this particular problem here. So I'll pause the video, have you pause the video right now and try this. All right, so hopefully you've had a chance to try and integrate this. And let's set up our table, and we're going to have positive, negative, positive, negative, positive, and we're not sure how far this is going to go down, but we'll just write that for now. In the second column, we've got u and du. So we're going to say u is equal to, you guessed it, x cubed. Why am I choosing x cubed for my u? Because its derivative ultimately gets down to 0. So I got 3x squared, 6x, 6, and then ultimately 0. Okay, so I'm differentiating down. In the next column, I'm going to start with dv, which would be e to the 4x dx, and then I'm going to start integrating. So this is going to be 1/4 e to the 4x. This would be 1/16 e to the 4x, 1/64 e to the 4x, and this is going to go on until 1/256 e to the 4x. Okay, so since I got a 0 here, I know I can stop integrating. So now I'm ready to put it all together. So let me just kind of zoom out a little bit and let's put it all together. So given what we have, let's go ahead and let's actually start by highlighting here. X cubed times 1/4 e to the 4x. That's my uv, if you will. So x cubed over 4 e to the 4x. That's my uv. Next, we got 3x squared times 1/16 e to the 4x. Keep in mind that I've got a negative here that I've got to apply. So negative 3x squared over 16 times e to the 4x. Then we got positive 6x times positive 1/64 e to the 4x. And then I've got negative 6 times 1 over 256 e to the 4x. And since I end up at 0 here again, I know that I am done. All right. So hopefully this gives you a pretty good sense of how to use the tabular method, which is a great approach whenever we have to do repeated integration by parts.